Hello and welcome to the little rover that almost did, lovingly known as T.A.D, and Group 13's presentation of the Lunar Rover Challenge. Now, in order to complete this challenge, the rover must adhere to a few basic constraints, such as weighing under 800 grams, conforming to a form factor of CubeSat U1.5, and collecting 3 samples in under 5 minutes. It then needs to carry those samples 10 millimeters above the surface, and should also be able to flip and detect rocks. For T.A.D's integrated design, he first takes in images using the Raspberry Pi camera, identifying and segmenting the different objects. He then starts to process their range and bearing parameters, and once these values have been processed and T.A.D has decided where to go, he sends this information to the motors for his wheels, and if T.A.D knows he is close enough to a rock or sample, he will lower his collection arm and move into collecting mode. In order for T.A.D to successfully collect samples and return them to the lander, he required a few key features, such as the ability to avoid obstacles, navigate to the closest sample, avoid walls, and navigate back to the lander. The method that was chosen to meet these key requirements was the artificial potential fields method, implemented in a local and reactive fashion such that T.A.D could be given the position of objects relative to his own and react to that data to find the correct path. This artificial potential fields method works by summing the positive and negative forces of goals and obstacles respectively to form a map of vectors. This method is most notable when T.A.D comes close to an obstacle and shakes his head, knowing he can't go near it, or when he sees a sample in the open and knows to go straight for it. T.A.D also had many failsafe methods that would allow him to break out of loops or local minima, such as moving away from an obstacle that is too close, or checking to see if he has collected a sample, and leaving it if it requires too many attempts to collect. These combined methods, as well as the use of a gyroscope, have then been used to allow T.A.D to operate within the testing field autonomously.
Hello, my name is Aidan and I was responsible for the vision system. The goal of the vision system is to provide navigation with accurate range and bearing to all targets in the robot's view. Firstly, the live imagery is converted to HSV color space, as this allows for greater precision when distinguishing similar colors. The image is then thresholded to generate a binary mask for each target, which is eroded and dilated to remove unwanted noise. This binary mask is then input into a contour detection algorithm, returning the bounding box size and location in the image. Finally, this information is used to calculate both range and bearing to all relevant targets, with the bounding boxes and relevant information displayed on the image output at a rate greater than 10 times a second. Simultaneously, the imagery system is also computing the general distance to the wall, displayed in the top right. This computation relies on the half-line transformation demonstrated in blue.
The sample collection subsystem went through two main iterations. The first, seen at the bottom left, involved a cage-like design that would automatically collect samples within a large area and secure it for transport. This involved actuators for lifting and releasing, as well as status sensors that would output if the sample was collected and the cage was open or not. The second was a scoop-like design with two extended arms that would be able to lift rocks and guide samples into a collection area. This scoop would only rotate to specific angles for collection and flipping rocks. This was the best option for this task. The scoop was controlled by a 9G micro servo motor. Due to its high torque and accurate rotational programming, this was the best fit to control the scoop. These were then placed below the camera in front of the robot. This allowed the status of the sample to be monitored by the camera. When collected, the sample was visible in the camera's vision. The sample was then able to be securely transported and deposited within the lander.
Hi, my name is Japneek and I am responsible for the mobility system. The mobility system is responsible for making the rover move around the surface and therefore is important that the design is robust. The rover uses a differential drive system with two 42mm by 90mm wheels and a 1.5-inch caster wheel, and was selected as it is inexpensive, able to easily maneuver, and provides increased torque and grip when climbing up an incline. Based on velocity and acceleration calculations, two medium power DC gear motors were used as they could achieve minimum and maximum forward velocities. These were controlled by a motor driver that sends direction and PW speed values from the Raspberry Pi. The chassis was designed in accordance with the basic stability and balance principles. All components were positioned in accordance with the triangle stability theory and were built in a double-decker design for efficient mechanical integration.
Thank you everyone for tuning in to the adventures of the little rover that almost did.